Okay, so I'm going to cover the entire chapter 2 here. It's a pretty big chapter, so buckle up. Here we go. So this first section, I'm going to talk about elements and which elements are common to living things, describe how ions form, and then how do atoms form bonds. So there are two types of bonds that they can form, ionic and covalent bond in. So all living things are made up of atoms, and atoms can exist in various forms, and we call those various forms elements. So atoms are the smallest basic unit of matter. If I ask you a question, what's the smallest basic unit of life, do not say atoms, because the correct answer is cells. So atoms are the smallest basic unit of matter, but they do consist of three subatomic particles: protons, neutrons, and electrons. And protons and neutrons are found in the nucleus of the atom, and protons have a positive charge and neutrons have a neutral charge. And you'll notice that with these positive charges here and here, you might be thinking, well, like charges tend to repel each other. I mean, if I take two magnets and I put the positive end towards the positive end, it's going to push away from each other. So how come the nucleus of this atom isn't, spontaneously pushing away or breaking down? Well, it has everything kind of to do with the neutrons. How neutrons have a neutral charge, and they just give it enough space so this repulsion force doesn't really take over. So neutrons act like the glue that hold the nucleus together. But the number of protons also determines the element that it is. So all carbon atoms have 6 protons. Okay, so like the number of protons you find in an atom will tell you what element it is. Like oxygen, all oxygen atoms have 8. Neon, all neon atoms have 10. Helium is 1 proton in the nucleus. Boom, you have helium, or not helium, hydrogen is what I meant to say, sorry. But yeah, so the number of protons you find in an atom determine the element that it is. Now outside the nucleus we have electrons, and electrons have a negative charge, and they are mostly responsible for chemical properties, how reactive this element is. And it has everything to do with kind of filling an outer energy shell, and I'll get more to that in this video. Okay, so an element is a substance made up of the same types of atoms. Compounds are substances that have different elements in it. So here I have some examples of compounds. H2O. Here I have 2 different elements, hydrogen and oxygen, chemically bonded together. CO2, carbon dioxide. Carbon and 2 oxygens chemically bonded together. So it's just a picture just showing, I have helium atoms, I have oxygen molecules. We'll talk more about molecules later on. But here's a compound where I have 2 different elements chemically bonded together. All right, here's some elements that you might find in your cell phone. Well, you find a lot of different metals. I mean, just look at your battery: lithium, cobalt, aluminum. Here we have potassium, and then we even get into the lanthanide series. So lots of different metals in your smartphone. All right, I'm just going to skip that slide. All right, here we go. Moving on to ions. So what are ions? Ions are atoms that have a charge. It could be a negative charge or a positive charge. And how they form are when atoms gain or lose electrons. So when we find an atom in nature, we just tend to assume that it's neutral. That means I have the same number of protons as electrons. If I'm looking at carbon, it's got 6 protons and 6 electrons. If you have 6 positives and 6 negatives, it balances out. So it's neutral, right? 0. So ions form when you get an imbalance of those protons to electrons. And they tend to form in atoms with nearly full or empty outer energy levels. Okay? What atoms really want to do is they want to have a filled energy shell. So here's just a quick chemistry lesson. Here's the first energy level. These rings represent energy levels. And so this first ring holds 2 electrons, and it always holds 2. Okay? You can hold 1, you can hold 2 is the max, basically. And then the second one is 8. 2, 4, 6, 8. And the third one's also going to be 8. So these rings can only hold, these outer 2 rings can only hold 8 electrons. And then once it's filled, you move on to the next shell. You put another ring. So here's sodium. Sodium had a dot here before. You can kind of see it's been moved over. So it has 11. And if I look at the periodic table, the atomic number, the number of protons sodium atom has is 11 protons. So that means it also has 11 electrons. And if I count these red dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then one out here, 11. So this was neutral. Okay, now let's take a look at chlorine. The atomic number is 17. So I have 17 protons and 17 electrons. So I'm going to count to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Now, chlorine needs one more to get to 8 to fill this outer energy level. And sodium would need 7 more to fill this. And so it's like, wait a minute. That's a lot of energy to be transferring electrons. It's just easier for me to get rid of this 1 and give it to chlorine, so chlorine can be happy. So now we have a full outer energy shell here. And sodium, which is over here, if it loses this 1, well, now this energy shell is going to disappear. And if we look at ring 2, it's completely filled. So we can achieve this filled energy shell just by transferring this 1 electron over from sodium to chlorine. Now, when you transfer that electron over, now we have an ion because the number of protons and electrons no longer balance each other out. So sodium has 11 protons, okay? But if I look, it only has 10 electrons. So 11 protons versus 10 electrons, I'm just going to have a positive 1 charge. And chlorine over here has 17 protons, but now it has 18 electrons. And so the balance here is I'm negative 1. Okay? So these are ions. These atoms have now become ions. They have charges because their protons and electrons do not match each other. They're not equal. When you transfer electrons over, you have created an ionic bond, an electrical force between oppositely charged ions. So I have this activity here looking at lithium and chlorine, where lithium, the number of protons is 3, so I'm going to assume I have 3 electrons. So I'm just going to drag it over, and we're going to see how fast my computer is, because it's been really slow. So there's 3, 2 in the first energy level, and then 1 in the second energy level. And now I had to choose chlorine, which is 17. Holy smokes. So 1, 2, 3, oh boy, 4, 5, 6, 7, 8, 9, and 1 more, 10. Okay, so this energy level is filled. Now it has 8. So now I'm going to move up to the third energy level. 11, 12, 13, 14, 15, almost there, 16. All right, 1, 2, 3, 4, 5, 6, maybe 1 more, 17. All right, so I have 7 in this outer ring, and chlorine just needs 1 more to get to 8. Okay, lithium would need 7 more, but that's way too much energy, so it's just easier to transfer this over. And when that happens, now lithium, which has 3 protons, now only has 2 electrons. Okay, so if you do the math, 3 positive minus 2 negative, you end up with a plus 1 charge. And chlorine over here still has 17 protons, but now the electrons went from 17 to 18, and now it has a minus charge because I have more negative particles than I do positive. Okay. So this is just another diagram showing sodium chloride. Okay, moving on. So one way to remember ionic bonds, the name's bond, ionic bond, taken, not shared, which means the electrons are taken or transferred. Oh my goodness. Okay, moving on to the second type of bond that you can form, covalent bonds. So atoms share pairs of electrons in covalent bonds. And sharing can also help us achieve fill in that outer energy shell. Okay. Covalent bonds tend to form molecules. Molecules of 2 or more atoms held together by covalent bonds. It can be the same elements, but it can also be different elements. And so what that means is that if they're sharing electrons, then you have created a molecule. And if they are being transferred, then you've pretty much created a compound, I guess. Covalent bonds occur because it takes way too much energy to steal 4 electrons, so it shares them instead. So it begs the question of going back to, like, what about the elements that are kind of in the middle? Like they're in the halfway point. So carbon, the periodic number is 6. So we have 6 electrons. So in the first energy level, I would have 2. I'd be 1, 2, and then I'd put 4 in the outer energy, 3, 4, 5, 6, right? And so it would need 4 more to achieve this. Well, geez, stealing 4 electrons or transferring 4 electrons, that's a lot of energy. So let's just share them instead. All right, so we're going to take it a step further. This is not in your notes, and it's not going to be on the test. So what determines whether an atom will form a covalent or ionic bond has everything to do with the electronegativity values. Electronegativity values tell you how attractive these elements are to atoms. And the higher number, which is fluorine, means that it's going to steal that electron or take that electron, versus lithium or sodium, which have low electronegativity values. So here you find the lowest values, and over here you pretty much find the highest values. So what you do is you take a look at the compound you're looking at, and then you do some simple math. And this is incorrect. I need to change this. But there are values that tell you what type of bond it's going to be, ionic or covalent. So, yeah. All right, moving on to water, properties of water. Okay, so we're going to talk about hydrogen bonds, why they're so important, and then explain the compounds that dissolve in water and compare acids and bases. So the properties of water. Life depends on hydrogen bonds, which is found in water. Water is tied to life. And the reason for that has everything to do with these hydrogen bonds. So we're going to talk a lot about these hydrogen bonds here, but water, first off, is a polar molecule, which means it has a slightly positive and negative end. It's kind of like a tiny little magnet. Nonpolar means that there are no charged regions, and they tend to share their electrons more equally. Here with polar, that means they're going to share their electrons unequally. So remember our covalent bonds from what I just mentioned a few minutes ago. Covalent bonds that means that those electrons are being shared. But if we look at water here, hydrogen's got 1 proton, 1 electron. Oxygen has 8. So I have 1, 2, 3, 4, 5, 6, 7, 8. So there are 2 open spots in oxygen. So it needs 2 more electrons. And hydrogen's like, well, we got 1. Let's share. So they're going to share these electrons, okay, and form this compound / molecule. But the cool thing about oxygen is that if I look back at my electronegativity value several slides ago, good gravy. All right, oxygen's 3.5 and hydrogen's 2.1. When I subtract 3.5 minus 2.1, okay, you get 1.4. And 1.4 means you're going to be polar covalent. You are going to share your electrons, but you're going to share them unequally. I'm just going to get out of this view here and do this because it's really, really slow. Oh, I had it on the next slide. Anyways, so you're going to share your electrons, but you're going to share them unequally. It's kind of like if I were to bring a pan of brownies, I could share it in 2 ways. I could cut up my pan of brownies equally and give everyone a piece. And I could say, I'm sharing my brownies equally. Or I can give you all tiny little slivers, and then the rest of the pan is mine. I'm still sharing, but I'm not sharing equally. So that's what happens with oxygen and hydrogen. Now, when you share things equally, you don't get a charged region. Okay? When you share them unequally, now you have a negative charge and a positive charge, basically a tiny little magnet. With ionic bonds, remember, we're taking electrons, or we are transferring electrons. So here's water. I can cut this molecule in half right here and get a positive end and a negative end. This over here with carbon and hydrogen, I can't cut this molecule in any way to get a positive end or a negative end, and same here, because they're sharing these electrons equally. So a way to remember the different bonds, think of electrons as bones. What would your dog or a dog do, in case you don't have one? I don't have one. So if it's nonpolar covalent bonds, you have 2 dogs of equal strength. If you have polar covalent bonds, that means that it's unevenly matched, but they are willing to share unequally. And ionic bonds, you get 1 big greedy thief, right? Okay. So with hydrogen bonds and polar covalent molecules, you get this rule of like dissolves like. That means polar molecules will mix with polar molecules. That means they'll dissolve. Nonpolar tends to mix with nonpolar. When you put polar with nonpolar, they will not mix. Okay, water is polar. Oil, fats, waxes, nonpolar. Mix the 2 together, you don't mix them together. They separate each other out. This is the reason why with polar substances, mixing with polar substances, they dissolve into each other. So like sugar and water dissolve, salt, water dissolve. That's because you're looking at two molecules that have charged ends, and they will dissolve into each other. Okay, so what exactly is a hydrogen bond? Now, a hydrogen bond is an interaction between a hydrogen of one molecule and a slightly negative atom of a different molecule. So it's not really a chemical bond, it's an attraction, because this hydrogen here is positive and this oxygen is negative, and so of course opposites are going to attract because they're like tiny little magnets. And when water molecules do this and temperatures cool, you get a nice crystallated structure. And if you remember from earth science way back in 8th grade, water in a solid form, which is ice, is a mineral. But when water melts, it's not a mineral. So we talked about what are the four things for a substance in order to be a mineral. It's got to be a solid, it's got to have a crystallated structure, and there's like two other categories I can't think of. It's got to occur in nature, naturally, and I don't remember the fourth one. But anyways, here, this is the reason why ice floats. Okay, we form this crystallated structure, some microscopic air pockets. It's less dense, it floats. So properties tied to hydrogen bonds. First off, high specific heat. Water, because it will attract to other water molecules, has high resistance to changes in temperature because it takes a while for them to kind of disrupt that attraction for each other. Cohesion. Water molecules will stick together. Okay, they stick to each other because, again, positive and negative charges attract. And as a result, you can create surface tension, as you can see here with this water beetle. And then we have adhesion, which is attraction among different substances. So not only that, water sticks to itself, but they tend to stick to other molecules that could be charged. Okay, so you're probably thinking, who cares? Why are these important? Well, without hydrogen bonds, water wouldn't even be on planet Earth. Okay, it would evaporate so fast we wouldn't even have liquid water, and life started off in water. Here's a diagram showing specific heat. So I know it's really blurry, but it says water takes about 30 times longer to heat than gold, meaning it stores about 30 times more calories. So if I take a kilogram of gold and a kilogram of water and I apply the same heat, hence the same size of flame, gold's going to heat up a lot faster than water. So water here has a high specific heat energy versus gold. All right, now, many compounds do dissolve in water because of the polarity of it. So we need to, things need to dissolve in water in order for chemical processes to occur. If you think about where you find water, water is pretty much everywhere. I mean, most of your cells are made of 60 to 75% of water. And in order, your cells carry out a lot of chemical processes. So those molecules, those substances that are used in those chemical processes have to be able to dissolve in it. So when things dissolve in water, you end up with a solution, homogeneous mixture of substances that is the same throughout. So the solvent is the thing that dissolves another substance, and the solute is the thing that does get dissolved. So here's my solvent of, we'll say it's water. Here's my solute, and I mix it together, and there's no grains on the bottom. And this solution is the same throughout, so it's a homogeneous mixture. So here's another example where we have water as a solvent, and maybe this is yellow sugar. I don't know why it's yellow, but we mix it, and we end up with a solution. Okay, some examples. Air is made up of roughly 78% nitrogen, 21% oxygen, and a mix of argon, carbon dioxide, and other gases. Which gas is the solvent and why? So the thing about mixtures and solvents, but basically, I want to say solutions, it doesn't have to be liquid and solid. Okay, it can exist in different forms. So here we have all of the gases, and I'm asking which gas is the solvent. And I hope you're thinking nitrogen, because there's more of nitrogen. So you can say nitrogen's dissolved in all the other types of gases. Brass is a metal alloy, a solid dissolved in a solid, typically 67% copper and 33% zinc, which is the solvent and the solute. So the solvent, in this case, would be copper because there's more of it, and the solute, the thing that gets dissolved, would be the zinc. Vinegar contains 5% acetic acid and 95% water, which is the solute. Boom, acetic acid. There's less of it. It's getting dissolved in the water. So hopefully that kind of clarifies some things. All right, some compounds do form acids and bases. Acids means you have a high concentration of hydrogen ions. The pH level is 0 to 6, and they tend to donate protons in that solution. Bases are the complete opposites. You have a low concentration of hydrogen ions. pH is 8 to 14, so a high pH means you have low concentration of H+, and they tend to accept protons. And smack dab in the middle of your pH scale is 7, which is neutral. So here we have acids Okay, low numbers, bases, or alkali, high numbers. And these are some examples that kind of line up with that pH. So acids, citrus fruits, tea, battery acid, vinegar, milk, soda, apples, bases tend to be common household cleaning supplies like baking soda, lye, ammonia, soap, and antacids. I read this statistic, like I think it's like 56 or 60% of incoming college students cannot name a single base, like an example of a base. So hopefully you're thinking, I don't want you to be a statistic, basically. So bases are cleaners. All right, here I have a pH scale, 0 to 14, and here I have these hydrogen plus. So remember, acids tend to have a lot of high hydrogen concentration, and bases have low. So what's the relationship between H plus concentration and the pH value? I hope you say it's inverse. So it means if I have a high number of H plus, my pH value is low. Or low number of H plus, my pH value is high. Okay, moving on to 2.3. Macromolecules. All right, so we're going to talk a lot about carbon and why that is the element tied into life. And so we'll talk about 4 macromolecules: carbs, lipids, proteins, and nucleic acids. All right, carbon-based molecules. So carbon, there's a reason why life is based on the element carbon, and it has everything to do with its unique bonding properties. Carbon's found in all living things due to its 4 valence electrons. We have 2 in the first energy level and then 4 in the second energy level. And so it can form 4 bonds because carbon tends to form covalent bonds. And carbon can form the 3 fundamental structures that can make up any complex molecule. It can form straight chains, as you can see here with propane and butane. It can form branched chains, isobutane, isopentane, or it can form rings, cyclohexane, cyclopropane. Large molecules are made of smaller molecules that are linked together. So some key terms I need you to know: monomers versus polymers. Monomers are individual subunits, and polymers are the large molecules that are made up of those monomers. So here I have a bunch of monomers, but if I link them together, I'm going to form a polymer. 4 main types of carbon-based molecules found in living things are carbohydrates, nucleic acids, proteins, and lipids. So carbs are sugars and starches. Those are the classic examples of carbohydrates. It has carbon, hydrogen, and oxygen, usually in a ratio of 1 carbon to 2 hydrogens to 1 oxygen. The monomer is called a monosaccharide. The polymer is a polysaccharide. And the most important function we use for carbs is energy use, but we can also use it for structural support, like cellulose. So here I have a diagram of starch. Okay, we have enzymes that recognize this glucose molecule. Notice the CH2OH is on tops. And so this enzyme might be like a Pac-Man and just like eat this, basically, or break this bond. But if you take a look at cellulose, notice the CH2 is upright, and now it's down here. And then it's upright, and then it's going to go down here. Well, we have enzymes that don't recognize cellulose. We can't break down cellulose. And so cellulose, which is found in the cell walls of plants, like corn or cellulose or celery, our body can't digest that. So if you just think about if you eat corn one day, a few days later, corn comes out of you, well, that's the reason why we can't break down the cellulose. All right, second macromolecule, lipids. Examples are fats, oils, and cholesterol, again made of CHO. The monomer, we call them fatty acids. The polymer is a lipid. And the function here is energy, but lipids make up the cell membrane of every cell. A cell membrane for any type of cell is made up of a phospholipid, 2 fatty acid tails, and a phosphate head. Third macromolecule is protein. So meat, beans, keratin, hair, nails, those are all examples of proteins. It's made up of carbon, hydrogen, oxygen, nitrogen, and sulfur. The monomer is an amino acid. The polymer is a protein. The function is that it does everything, like eyesight, digestion, a whole bunch of different chemical reactions, like protection. It actually can help carry out chemical reactions. You know what? I feel like I'm showing you the wrong slide. This is driving me insane. Sorry, Kenny. Sorry. I just feel like this is not the slide. And it's not there. But according to this, it's 2018. Oh my god. This can't be. I just remember a different slide. Yeah, I don't know. Alright. Okay, if the notes aren't lining up, I'm sorry. But moving on. Okay, nucleic acids. The fourth macromolecule. Some examples of nucleic acids, DNA and RNA, made up of carbon, hydrogen, oxygen, nitrogen, and phosphorus. So the monomers here, nucleotides like A, C, T, G, U, link them together, you're going to make a nucleic acid. And the main function for nucleic acids is to store genetic information. Yeah, see, I feel like your notes are not going to line up because I thought I listed off elements that are common, and we talked about trace elements, and I had like a thing about a pirate, and I can't find that PowerPoint. And I don't know why I can't. Most of it's the same, but there are a few modifications. Okay. Moving on to chemical reactions. So a chemical reaction is when you change a substance into a different substance, either by break-in and reforming bonds. Anything that goes into a chemical reaction we call reactants. Anything that comes out of a chemical reaction we call products. And so here we have the classic example of cellular respiration. 6 oxygen molecules plus a molecule of glucose yields 6 molecules of CO2 and 6 molecules of water. If I were to count up all of these atoms on this side and compare them to this side, they would be the same. So like carbon, there's 6 carbon atoms on this side. I have 6 carbon atoms on this side, so you would distribute this through. So 6 times 1 is 6. For oxygen, 6 times 2 is 12, plus 6 is 18. 6 times 2 is 12, plus 6 is 18. So the oxygen matchup. Hydrogen, I have 12 here. 6 times 2 is 12. So you're not throwing in any new elements. You're taking what you are given and you are rearranging them in a new way and coming up with new products. So reactants are what goes in, products what comes out. All right, bond energy is the energy needed to break or form a bond. Whatever energy is needed to break that bond is going to be the same amount of energy to form that bond. You just swap the sign. Okay, so you can see that there. Okay, reactions are reversible, so we call that chemical equilibrium when they can go in both directions. So it has everything to do with the concentrations of reactants. So if I have a high reactant concentration, then it's most likely going to flow in this direction so I can make more products. If I have a high number of products and the reaction is reversible, then it will flow in the opposite direction. You can see here with the big arrow. But if they have equal amounts, then I'm going to have equilibrium. Okay, activation energy is the amount of energy that needs to be absorbed for a chemical reaction to start, aka like the energy to bike up a hill, but then once you go down the hill, then you're not really using any energy. So activation energy is really important in order to jumpstart a chemical reaction. I see that I'm missing a slide with frogs and an analogy. But anyways, here's my reactants for, again, cellular respiration. If I don't have any enzymes or anything helping it, notice the activation energy is really, really high. Well, I'm going to segue into enzymes. Our body is filled with different enzymes that help lower that activation energy so the reaction can occur more readily. So an exothermic reaction is any reaction that releases more energy than it absorbs. So if the products here, A plus B produces C plus D, if the products are lower than the reactants, it's going to give off this amount of energy. And the opposite is called an endothermic reaction, where it absorbs more energy than it releases. And our products have more energy than the reactants, and this is the energy that's going to be absorbed. Okay. 2.5 is all about enzymes. So if you leave a newspaper in sunlight, eventually it's going to turn yellow. If you set a match to a newspaper, it's going to burn. What does adding energy to a chemical reaction do? Well, it's going to increase the kinetic energy of the reactant molecules, and they're going to move faster and faster and faster and collide with each other. As a result, end up with a faster reaction. So adding energy to a cell could destroy a cell, So a solution to this is to lower the amount of energy needed to start that reaction by using enzymes. So another word for enzymes is a catalyst. Catalysts decrease activation energy. They make that hill on that graph lower. So they, as a result, when they lower that activation energy, the rate of the chemical reaction is going to increase. Catalysts or enzymes take part in the reaction, but you don't see them on the reactant side or the product side because they're not used up or changed during that reaction. So here's a sketch just showing if I don't have a catalyst, I have a high activation energy. But if I add a catalyst, it's going to lower that activation energy and increase the rate of that chemical reaction. So here's that frog diagram that I was talking about. I don't know why they use frogs, but imagine this high barrier as my activation energy. If I have no enzyme, boy, this frog is really going to have to jump in order to get over that barrier to get to the product side, which are wet frogs. However, if I have an enzyme, they're basically going to take away these rocks and lower the energy barrier. So now the frog doesn't have to work as hard to get into the pond and become wet. So enzymes are catalysts for chemical reactions that are found in living things. Basic kind of functions that they do, they lower activation energy, that's the abbreviation for AE. They increase the rate of the reaction and cause it to happen a lot faster, and then can help reverse reaction as well. Enzymes are proteins, okay? So it depends on their structure to function properly, and I'm going to talk a little bit more about that, what happens when you mess up the structure of an enzyme. But the environment here can alter the structure. If you increase the temperature or decrease the temperature, the enzyme shape is going to change, and it's not going to work right. And I'll explain here in a minute. Or if you change the pH, how acidic or basic it is, it's going to alter the shape of that enzyme. So first off, think of enzymes as like locks and keys. They are very specific, and they only work with certain substrates. So you can see here that this enzyme is only going to work with these two rounded substrates. Substrates are the substances that bind to an enzyme that it acts on. This enzyme over here is only going to work with this blue and this pink piece and bond together. Now, if you increase the temperature, okay, well, maybe now it's not going to become round, it's going to become boxy. And so now this round green sphere won't bond properly to it, and this enzyme will be faulty. A lot of diseases and syndromes that people experience have to do a lot with their enzymes not being folded or put in, like, their structure is incorrect. Either, I'm not saying because of temperature or pH, it could be due to genetics, but I'm just saying you can mess up enzymes by changing the temperature or the pH. And that's kind of what we did with our liver lab. But anyways, an analogy for enzymes, active sites, the things where the substrates lock onto or bind to, are like the locks. And the substrates are the keys that go into the locks. And if you change the pH or the temperature, you're basically changing the lock, and the key's not going to fit right anymore. So here's an example of a glucose enzyme. And it binds specifically to glucose, and when it does, it usually goes through a change conformation. Okay, there are 4 steps in the process of an enzyme working. Number 1, the enzyme and the substrates are in the same area. 2, the substrates will bind to the active site on that enzyme. And then 3, the enzyme's going to be changed. Either it's going to break bonds or form bonds, and then once that happens, the enzyme's going to let it go and find more substrates. And so you can see here, enzymes are not products or reactants. They're kind of like chaperones. They help the reaction occur, and then they just kind of get out of the way. So you don't find them on the reactants or product side. So that does it. Now, we did a lab with liver, where we took liver and we subjected it to different pH values, and we looked at the enzyme level, and we noticed that really, really low pH, the enzymes didn't work correctly. We didn't get a lot of foam height. So you saw little foam height, and then if we increased the pH, we saw higher foam height. That's typically how it went. So sorry you missed out on that. It's good luck. All right, that was chapter 2. I did the entire chapter 2 for you. I hope it was helpful. But really, I just need you to take notes and take the test and score above 60% on both of them. And good luck.